Professor Stephen Liang. Professor Liang is the Morris Bryan Professor in Mechanical Engineering for Advanced Manufacturing Systems at Georgia Tech. Dr. Liang began at Tech in 1990, and prior to that, he was a professor at Oklahoma State University. He was also president of Walsen Liwa Corporation in 2008 to 2010. Dr. Liang's research focuses on precision manufacturing processes in the context of modeling, monitoring, control, and optimization. And he's won many awards, including the Milton C. Shaw Manufacturing Research Medal and the Society of Manufacturing Engineers Gold Medal. So Professor Liang is a very distinguished professor in manufacturing, and we're very pleased to have him talk with us about spacecraft manufacturing. So welcome, Professor Liang.
Thank you, Glenn. Thank you, Wenhui. Okay, so Glenn's introduction reminds me of an occasion that I went to a couple of years back. There was another conference presentation. The chairman actually introduced the speaker by saying, today we have the speaker from California who's in the business of computer manufacturing and make a profit of $10 million just last year. So he asked the speaker to start presentation. The speaker just said, "Oh, thank you, Mr. Chairman, for your very nice introduction of me. But I would like to make some minor corrections. First of all, I'm not from California. My location is actually in Texas. But that's fine. But there's another minor correction about what I do. I actually don't make computers. I make computer furniture, computer desks, computer chairs, and things like that. And by the way, the $10 million number was not exactly correct. The number for last year was $100 million, much bigger, $100 million US dollars. One last correction I would like to make is that the profit that the chairman mentioned was not exactly correct. That was a loss last year. So that Glenn's introduction reminded me of that occasion, although his content of introduction perhaps is not that much off. But my name is Stephen Liang. I'm a Morris Bryan Junior Professor. For advanced manufacturing, I need to make a notification that this word junior is associated with my donor's name, Morris M. Bryan Jr. It's not associated with the professor. I'm not a junior professor anymore. Maybe a couple of years ago, I was a junior professor, but not anymore. So I'm going to talk about first and every part right, subtractive and additive manufacturing and aerospace and aeronautical applications. And I'm very honored to be given this opportunity to talk to TSU through this smart online course platform. And I look forward to many other speakers going forward from here. And we have been at Georgia Tech, we have been collaborating with a large number of partners. Many of them are in aerospace, aeronautical industry, and some of them in automotive, some of them in energy, and some of them in critical component manufacturing supplier segments, and of course some government agencies, including National Science Foundation and Sandia National Laboratory, Los Alamos, NIST, and so on and so forth in the US. And as far as aerospace applications, we are interested in the aspect of manufacturing. So a lot of the content that I'm talking about today is about manufacturing. I'm not going to get into much in the field of design and functionality of aeronautical and aerospace industry attributes, but I'm going to focus on manufacturing. And I would probably try to touch upon some scientific content, although my main focus is on engineering applications as much as possible. As far as the aerospace industry application challenge, we're talking about several of them in aerospace application manufacturing. We are always required to do multi-objectivity manufacturing. This is to say the objective is not only the quality, or it is not only the cost, but a QCDS, a QCPS, and full array of them. And most of them are contradicting with one another. And in most of the cases, we're not going to do things like this will work. Okay, and as a matter of fact, we're always pursuing the mentality of this will work the best. And the maximality is very important. And what we do at Georgia Tech is not just to satisfy laboratory applications, but we want to make sure in application industry settings, it will work consistently. Right? So it's the predictability and certainty is very important. And every time the user in aerospace industry changes their material, changes their design and functionality, the manufacturing has to be able to switch over very fast in an attempt to shorten the process development cycle for first and every part correct manufacturing. That's what we're trying to do here at Georgia Tech in the field of manufacturing. And we have been involved in quite a bit of effort on process issues related to the modeling, improvement, optimization, as well as the development of new processes. We're also interested in the sustainability issues, quality issues, and their relationship, manufacturing relationship to materials. That much said, let me get into the details of several examples in the field of subtractive manufacturing, the work we have done at Georgia Tech. Most typical example is the use of computer numerical control machine tools for manufacturing. But that technology has been around for several decades. With the use of sensors and controls, actuators, we'll be able to close the loop. Let me maybe pop up my pointers. So we maybe close the loop with the use of encoders and tachometers to put the part program requirements in terms of feed, speeds, and position under very tight closed loop control. However, if you sell a product to your customer to say that my manufacturing fees, speeds, and depth of cut is very well controlled, nobody will buy that argument because your customer is mostly not interested in the part program. Instead, they are more interested in the quality. They are most interested in the manufacturing cycle time. And a lot of the defects, a lot of the unexpected disturbances in the manufacturing process, for example, tool wear, chatter vibration, runout, eccentricity, deflection, thermal expansion. These are the things that will be fighting against part quality. And they are absolutely, they are actually represented by the tool and workpiece interactions, absolutely outside of the computer numerical control feedback loop. So the computer numerical control loop has been found quite inadequate to satisfy the precision and functionality requirements at this current point of technology. So we are into smart manufacturing. Smart manufacturing is to use a whole bunch of higher level sensors to measure temperature, vibration, acoustic emission, and machining forces. And that monitoring signal will be sent to a smart analytics processing module so that the requirements of the part function and performance in the context of perhaps dimensional accuracy tolerance, surface quality in terms of finish, and the productivity in terms of throughput can be put into a control loop to modify the machine feed speeds and depth of cut to generate a bigger and more encompassing smart machine tool intelligent platform that surrounds the traditional CNC system. In this way, the tolerance, finish, and throughput can be very tightly controlled afterwards. This tolerance, finish, and throughput are exactly what the customer would like to have, would like to see. And some couple of examples. What I'm going to talk about today will be just examples after examples of some of the work that we have done with aerospace company like Pratt & Whitney and Boeing over the years. And this example of a surface grinding operation, because of the variation of contact area between the grinding wheel and the workpiece surfaces, during the feed motion of the grinding wheel, the grinding force will vary, and as a result, the actual depth of cut will change because of the flexibility of the creel height, the machine tool, grinding machine tool structure. So if you, most of us have this experience, if you grind a part left and right, and then left and right again several times, so the two shoulders will get ground off pretty fast, and the center portion will be bulging out. That is pretty much because of the flexibility of the machine tool structure itself. So what we have done is to close the loop by measuring the instantaneous deflection of the workpiece and the grinding force, in coupling with the actuation and control, feedback control of the creel height of the grinding wheel, so that when the wheel gets to the center portion of the workpiece, it is pressed downward a little bit more to compensate for that loss of depth of grind. And this picture shows the dotted line with a grinding process without the smart feedback control, and the solid line is the surface of the ground part with the smart feedback control in a different set of process parameter. The result is shown to the right. And this is another example, not in the surface flat grinding process, but a cylindrical grinding process, where typically, maybe in everybody's daily experience, we typically experience error coming from transient positioning error, as well as steady state final in-feed error. So what we're trying to do is to control the grinding power at a optimal level. That would guarantee the G ratio to be maintained at a value that maximizes the material removal rate with respect to the tool wear rate. And we found that the power is quite sensitive to the velocity. Power is not a controllable parameter in the real manufacturing process, but velocity is. So we'll be able to look at this example on the very right end of this workpiece that has different areas of surface height. And the power is what is measured, the grinding time, and the part quality is the objective penalty function, and the process parameter of velocity is set as the controllable variable. In this case, the velocity will automatically drop down to a low level when it grinds, when the wheel grinds into a thicker portion, and will pick up again when it grinds to an intermediate portion. So time is not wasted, and dimensional accuracy is very much secure. Out of this smart grinding operation, we're typically looking at the very least 30%, 40% savings in the process time. And another example is this end milling multiple fluid machining operation. Many of you have this experience that the cutter is often known to have certain amount of eccentricity, what we call the runout error. And so the cutter will likely to wobble in real life. When the cutter wobbles and cut at the same time, the workpiece surface or the dimensional of the workpiece will suffer, and you typically see the formation of those scallops on the finished product, very undesirable. And if this is put into the engine of a airspace vehicle, then the horsepower or the thrust force would be compromised. In this situation, we have been working with a company in industry to put this workpiece on a piezoelectric crystal actuated work table. And that work table forces the workpiece to move in and out several cycles per spindle revolution duration. A spindle revolution runs at very high RPM, so as the PZT actuated table. So the table is forced to dance with a wobbling cutter. So if we are little enough to stand on this workpiece and observe a wobbling cutter, the observation would tell you that the cutter is perfectly true without any eccentricity. So that is the result at the bottom of this slide to show that without this, what we call the smart chipload servo control, the surface that come out of multi-flue milling typically has cutter marks. And under the same set of process conditions, the cutter mark can be 70% to 80% reduced, not completely eliminated, but drastically reduced without sacrificing any processing time. And there's another example of micro-scale manufacturing with a small footprint machine tool. Production machinery. So on the left is a traditional multi-axis CNC system, typically with a linear side dimension of 2 to 3 meters, and we reduce that to about 1/10 of a meter in the side dimension. That is a size reduction of on the order of 10,000 times. Not just the size of the machine is reduced, the depth of cut in a traditional setting is on a machine on a subtractive manufacturing configuration is about 1 micron, and we reduce that down to perhaps 1 nanometer. Okay, that is about 1,000 times of a reduction in the accuracy. So this one has a lot of interesting application. For example, in the battlefield application scenario, if the troop is fighting in deep mountain or large desert environment, lots of the part of the equipment, battle equipment, will unexpectedly lose their function because of all sorts of possible problems. And it is very difficult for, if we have a tank that has a missing gear, a broken shaft, and then that shaft and the gear will have to be sent back to a home maintenance facility hundreds of miles away, and that is physically not possible. So the equipment or the vehicle will basically go unusable. But with this, in this military scenario, the military has developed what is so-called a parts hospital to have a truck, small, medium-sized truck, to accommodate 8 to 10 pieces of machine tools, some grinding, some turning, some drilling, with very small footprint. So you'll be able to make maintenance and make repair on the site, right where the vehicle is sitting. In aerospace and aeronautical applications, within application scenarios, within a very limited space of a spacecraft interior, it is very difficult to imagine that you put in a traditional machine tool, a couple of meters by couple of meters by couple of meters in footprint. But with this micro-scale manufacturing capability, all of a sudden we're able to put maybe 5 machine tools, or even 8 or 10 machine tools, some doing drilling, some doing milling, some even doing additive manufacturing within the spacecraft limited space. So that would all of a sudden increase the capability of manufacturing, not only by miniaturization of the production machinery volume, but also by increasing the accuracy and precision of the manufacturing process, because of the fact that thermal stiffness and static stiffness, and as well as the dynamic stiffness, they all increase significantly with the reduction of machinery physical volume. So we have looked at the application of those, and some of the work that we have done is the knee and column type of vertical machining center, as shown in this picture at the center. We actually make this center, this machine tool, micro-scale machine tool, and put a couple of them in Taiwan universities and research centers, several of them, with a 300,000 RPM spindle capability. That's more than 10 times faster than the state-of-the-art high-speed spindle. And this system has 1 micron runout accuracy, okay, extremely accurate. In-bar structure with high thermal resistance, and with a cutting tool two flute solid carbide cutting tool of only 5 to 10 micron diameter in comparison to a human hair. This is only 5% or even 3% of a human hair diameter. Of course, you can imagine that it will take to cut your hair, to go to a barber shop, cut your hair with this cutting tool. That may take you a full day to finish that hair cutting cycle. We also have done not only the knee and column type, but we also have put out some gantry type of milling machine, okay, on the market. The cutting tool is so small that most people do not get to see the cutting tool at all. So my assistant sometimes said there's actually no cutting tool while the cutting tool is indeed in place. If you look at a cutting tool hard enough, the cutting tool will probably break by your looking at it. So a cutting tool is very small, and to find the cutting tool, we need to resort to optical measures using these laser locator to find the tool height, to find the tool position left and right, as well as the use of acoustic emission sensors to identify the contact of the cutting tool with the workpiece. So that is a microscale cutting tool. And there's another example of what we do for precision grinding. Traditionally, in a conventional way, grinding is used to create large and flat and smooth surfaces. If the surface is small, the surface is curved, the surface has slot and holes and small re-entrant details, and the surface will be very difficult to grind successfully. And what we have done is to use the following, what is called a single particle magnetoabrasive machining, to take one grinding particle out of a grinding wheel and put it under very high level of electromagnetic field for some time. So this particle taken out from the grinding wheel, this particle is magnetized, and it has north pole and south pole. Magnetized in this case is a El Nico particle. In this case, since it has poles, it's polarized, so we'll be able to put it in a magnetic field so that it will rotate with the field. And if we put this rotating particle in contact with your workpiece, the workpiece is making multi-axis CNC control motions at the same time, then cutting can begin not only from the outside surface, but also going into the inside surface to create inner details as well. So this allows us to do micro scale cutting that facilitate what is called the ductile mold brittle material machining. So we'll be able to cut ceramic, cut glass relatively easily without breaking the workpiece. Of course, like what I just pointed out, the ability to cut internal details and minor micro scale features is quite important. And this is how we did it. So particle, the magnetized particle is first of all suspended in the free air, and with a horizontal magnetic field of a constant voltage applied. And there are two other electrical, the AC connected electrical loop, okay, that is alternating in time with a 90-degree difference, the phase difference, so that the resulting magnetic field will point in a direction, this little m, that is actually changing with time. So this little magnetized particle will end up chasing after the rotating magnetic field and tirelessly and rotate at a couple of thousand RPM and begin to be able to grind. Okay, so in the area of subtractive manufacturing, we have done a couple of work to look at different process behavior associated with the workpiece, how high the temperature will go. This is important because the workpiece temperature will affect the dimensional accuracy, warping, and distortion. How much force that is taking, it will determine the required payload of your manufacturing equipment, how much the workpiece is likely to chip, or that is super essential for some applications that involve very hard material, and for example, ceramic material a hard, high carbon steel material that's easily cracked at the tip of the tool and compromise the part quality. And we also worked out a process map to show exactly which of the depth of cut velocity process parameter range the workpiece will be burned, and a couple of, and also show where are the areas of operation that the material will be just fine. And we also look at the prediction of residual stress out of machining. We'll talk about residual stress in just a minute, if I still have time. Precision machining also, our work also look at the behavior of cutting tool in terms of the wear pattern of the tool, in terms of the aerosol that is generated by the cutting tool. So if you go, that this is also in everybody's not so pleasant experience, that if you go into a machine shop with lots of machine tool running, that you typically unavoidably will smell the taste of a cutting fluid in the air. And that cutting fluid, the smell is relatively bad for the operator lung, respiratory system, or even the skin. So we have worked with a lot of industry company to look at the control of process parameter in order to curb the generation of cutting fluid aerosol generated from several mechanisms of cutting fluid splash, cutting fluid spin-off, cutting fluid evaporation, cutting fluid perturbation in the air, as well as the consolidation. And the cutting fluid turned out to be quite effective already without using the wet mechanism. So what we have developed here is a near dry machining NDM, just to spray very small amount of cutting fluid in the cutting zone. The effect to protect cutting tool would be just as good. And so this is the use of a minimum quantity lubrication to maximize the performance of machining. Of course, we also look at a couple of tool wear patterns and tool wear distribution as a function of location on the tool, as well as the combination of process parameters. So we look at also the materials relevance to manufacturing, to look at the microstructure attributes of workpiece and how that is changed by the process of machining. And here is an example that shows when the shaping or scraping operation is implemented on the workpiece, then we're able to analyze the variation of grain size. On the left picture, the grain size is relatively large, comparing to the grain size inside of the chip. As a result, the hardness or rigidity of the workpiece is relatively low, comparing to that of the cut portion, as well as on the chip. And with the analysis at the microscopic microstructure level, we call the viscoelastic self-consistency analysis. We're able to predict what exactly is going to happen to the workpiece when machining operation takes place. For example, on the left-hand side, we have a set of pole figures taken on the uncut part as a raw material. Then when the material is cut into the final product, its microstructure crystallographic orientation is shown on the right-hand side. And that is modeled by our analytical predictions in comparison to experimental measurements on the left. In terms of the inverse pole figure in the middle row, as well as the orientation of the distribution function. Orientation distribution function basically represent the features of the texture before and after cut. We can see that, for example, if I get rid of this thing, okay, if I may let you hide. Okay, for example, the inverse pole figure has a maximum intensity before cut of 2.28, and it dropped to below 1.9 something. Very well predicted with our model in comparison to the actual machine parts. Average grain size drop by machining dramatically as predicted and very well compared to experimental measurement. The hardness of the part increased significantly by machining, very well predicted and very well compared to experimental data. So this goes against the fundamental understanding that the machining or subtractive manufacturing process is typically done to change the shape, but not the property of the workpiece. The property is changed by heat treatment or other methods, but this is not the case here in our study, and this changed people's mindset and create people's imaginations. Residual stress is also very important when a part is cut, because residual stress is so influential to a part distortion, a part deformation, as well as the fatigue endurance in repeated loading situation, and it also affects the part resistance to corrosion. So in our analysis, the residual stress is very difficult to predict, right? Analytically, people do a lot of repeated trial and error experiment work to understand how much residual stress will be ideal. I've talked to a aerospace manufacturer in the U.S., and they sponsor a lot of our work and say that their turbine blade that they make is about 15 to 20 times more expensive than a third-party copycat turbine blade product. But their turbine blade can last a good 4 years, 5 years. But the copycat turbine blade will last 2-3 months, and it will break. The geometry of the turbine blade, the material of the turbine blade, Ti-6-4, are all exactly the same. The difference in the performance is in the residual stress, because the copycat duplicate my sponsor's geometry and materials, okay? But they cannot duplicate my sponsor's residual stress, because residual stress is intimately related to the process parameter and process conditions that you cannot duplicate as a competitor. So you need to understand how is a residual stress created, and we have done a lot of work for American aerospace industry to look at the mechanical loading, cutting force, as well as the thermal loading in terms of a temperature effect, and come up with the kinematic hardening and incremental plasticity analysis to predict the residual stress quite nicely. And this is a line of our prediction in blue color in comparison to our sponsors' experimental work that was done independently in red color, and they turn out to be quite similar in different directions, cut and axial direction, as well as in with the use of different materials. And what is also quite important is the reverse engineering process, right? If the user or the technology user is interested in knowing what type of a combination process parameter, what is the choice of a depth of cut and the tool geometry that will guarantee the residual stress, then the analysis is totally reversed. In our case, we are able, because of our analytical model is a completely analytical, physics-based, and enclosed form, we're able to reverse our analysis to use residual stress specifications, for example, compressive residual stress at the surface to how much depth, and these residual stress performance specification as the input. And then the calculation will come out to advise what would be the best choice of a depth of cut in the cutting tool geometry and so on and so forth. And this is a validation of what we do. Our sponsor actually implemented the dark blue color part residual stress distribution, but they did not tell us what was the process parameter that was used to generate that. And they asked us, they give us this blue dark line as given input and run our program to that will offer the combination of process parameter, and use that set of process parameter to do physical cutting one more time to generate what is so-called residual stress in the reverse process red line. They come out to be quite similar to one another. Okay, so I don't have much time left, maybe a short 10-15 minutes to talk about additive manufacturing and what we have done. at Georgia Tech. Of course, additive manufacturing is done on many different choices of material, like fluid material, paste material, powder, solid material, or film or paper or sheet material. And we have done quite a bit of work at Georgia Tech based upon the laser fusion of powder bed as well as powder feed configuration to generate different geometries. And this is an area, the additive manufacturing for metal. Now, we don't do much on the polymer and ceramic and composite. We do exclusively study for metal. As this is just the metal has been growing at a pace of 15% every year globally, and in the APAC region, we see 18% growth, and this is tremendous. It's hard to see any industry that has that much of a growth. If you put your money in the bank for 1 year time, you will be fortunate enough to get 1% back, and this growth in additive manufacturing is much higher than that. In aerospace application, there's a full array of different applications of a part, component, and design that contribute into the growth of additive manufacturing. Additive manufacturing is also quite important for the cost aspect of it. In the old days, these critical parts are probably mostly machined to maintain its part geometry accuracy, and waste a lot of the material in the form of a chip. But nowadays, the aerospace is talking about a buy to fly ratio, and the waste of material is definitely a big thing to be avoided. And why is this additive manufacturing so important? I'm sorry, let me take it back. And what we're doing is the predictive modeling for additive manufacturing. Why is predictive modeling or the prediction capability so important for additive manufacturing? It's because the conventional manufacturing, for example, forging, casting, rolling, these processes typically has a much larger batch, and many parts is created. So you would be it would be justifiable if you spend 3 hours of time just to develop the correct die geometry, the correct combination of process parameter. If you have to do a mass production, that would take 50 hours, if not 500 hours. But that's not the case with additive manufacturing. Additive manufacturing, you are producing 1 part or 2 parts, very low quantity of production. The total production, if it's only 5 hours, then how does it make sense to spend 3 hours time just to do trial and errors and repeated experiment just to come up with the best process parameter? So you should be able, in the case of additive manufacturing, the only way you can survive in this business is that you are able to do accurate prediction, so as to do first and every part right, okay, without trial and error and exhaustive experimental repeated testing. Okay? And so far, the bottleneck, the way the industry goes, is that the additive manufacturing, there's a lack of prediction tools. The prediction tool can be developed, of course, by a large amount of offline, upfront experimentation, but that takes tremendous amount of time. People do numerical simulation as well, finite element, but that simulation, for those of you that have some experience with finite element calculation, it takes tremendous amount of time as well. For a single scan track of laser fusion, the numerical simulation with ANSYS would easily take 3, 4, 5 hours. What we're trying to do is computational mechanics of material calculation for prediction of additive manufacturing performance and quality, so as to predict very rapidly and systematically and accurately. And in this configuration of, for example, the laser powder bed fusion process, if we're given the material property, given the scan strategy, and the combination process parameters such as layer thickness, the build geometry, and so on and so forth, we'll be able to predict the thermal history in the process cycle T, And from there, we'll be able to predict the microstructure attribute in terms of the S as the structure cycle. And then subsequently, we're able to predict the mechanical behavior in the performance cycle. This is the PSP the prediction cycle. So we're able to predict the in situ real-time temperature distributions during the laser fusion process. And accordingly, we're able to predict the thermal stress and thermal strain profiles and come up with the predicted microstructure in the context of grain size, crystallographic orientation, and phase field. And also, we're able to predict the residual stress as a result. And from the residual stress, we're able to predict part distortions and the formation of porosities, vacancies inside of the printed part. And we're able to predict the part quality, okay, because we have the microstructure information already predicted. We're able to predict the quality of or property in terms of the strength, in terms of hardness and elastic and plastic modulus as well. And this is all based upon the thermodynamic and heat transfer analysis of the additive manufacturing configuration. So we're able to build our prediction based upon the given inputs of process parameter and the powder material configurations and calculate these attributes of our interest in the form of algebraic physics-based explicit and closed form solution to describe the output. And this is, well, a lot of people will say, why do we not do finite element analysis? We actually at Georgia Tech, we're probably the only group internationally, or the only group that does not do finite element simulation. We do physics-based computational mechanics modeling, and we intentionally avoid the use of finite element because our model is much faster than finite element, faster than a couple of thousand times and much more accurate. And we are able to predict microstructure. The finite element doesn't do that. We're able to reverse our calculation and computation. Finite element cannot reverse. Okay, I do not know if you can do it, but I certainly cannot reverse a finite element calculation. But with our physics-based analytical closed form solution, we can easily reverse our calculation. So using these material and these process and laser configurations as input, so we'll be able to look at a Lagrangian distribution of energy conservation to come up with a what is called a movie heat source model that describe the temperature distribution, even considering the part boundary loss and the geometry effects of the build part. And from this thermal stress analysis, we try to describe the effect of repeated heating and cooling during laser sintering, the laser fusion process with the use of a Green's function of stress to characterize the in situ elastoplastic thermal stress and thermal strain, including the surface tension, body forces, and hydrostatic stress, and be able to use the kinematic hardening and incremental plasticity to calculate in closed form without any time spent for the residual stress left in the printed part back into room temperature, and to calculate the microstructure grain size and porosity. And in the interest of time, part distortion, I'm going to skip those analytical details and look at the results of our temperature profile calculation. This result is absolutely not coming from finite element. This is calculated from our MATLAB code that can be done completely, even with your pocket calculator, completely done. Able to be done in a closed form. So the temperature distribution shows that the temperature in laser fusion configuration shoot up extremely fast from a room temperature all the way to a couple of hundred, over 1,000 degree Celsius, very high temperature within a matter of 300 to 500 micron distance. And the laser irradiation point is this A point, and the laser scanning direction is from right to left in this lower right picture. Then the B point and C point at the equal distance away from the laser exposure point will have different temperature showing. This is because the B point is already preheated, so it has a higher temperature, and the thermal property and mechanical property of B point is drastically different from that of the C because of the temperature difference. So this is what we call a moving heat source solution that can describe the temperature profile pretty successfully. It's very difficult to measure temperature in real time during the laser fusion process. A couple of thousand for Ti-6-4, it goes to more than 2,000 degrees. But we managed to do some pull out teeth and measure several points of temperature in comparison to our analytical model. We also look at an easier way of measuring the heat affected zone, the melt pool geometry, and compare that. Melt pool geometry is easier to measure and compare to our analytical prediction to quite a close agreement. This is how we incorporate the effect of boundaries. And we look at the effect of scan strategy on material property. There's a larger scan strategy as well as a longer time delay within the different scan tracks will then reduce the temperature and reduce the specific heat and thermal conductivity of the material. And this is a picture that shows the thermal stress distribution and with a higher scan speed, the thermal heat deposited into the material reduces, and therefore the stress, normal stress in the build direction, normal stress in the scan direction, as well as the shear stress also approaches zero quite sensitively to the increase of scan speed. And this is a picture of a residual stress. And do I, Glenn, do I have another 5-minute time to wrap this up?
Yeah, I mean, I think we have maybe 10 more minutes for your talk plus questions. So 5 and
okay.
5.
Okay, thank you. This is a picture of our calculated residual stress in comparison to experimental validation in red circles. It shows that the surface layer where the melt pool depth, this is the very last surface layer that is scanned over, always shows a tensile stress. Okay, very undesirable for aerospace applications because that suffers from the initiation of cracks under repeated loading. And this is because of the fact that the last layer is cooled and solidified very last, and so it suffers from its immediate lower layer holding it back from contraction. Therefore, it's put in tensile stress. Then also it agree very well with people's experience that in a repeated loading situation, the crack initiation location is typically not exactly at the top surface, but at the 300 to 500 micron subsurface. And from this prediction, we come to realize that 300 to 5 micron 100 micron subsurface location is where the largest tensile stress is typically predicted. And this is how the stress is sensitive to the process parameter of scan speed and laser power. And I'm going to skip those. The effect of process parameters, hatching space, and all that on the resulting residual stress. It is also quite interesting to see that the preheating, a lot of people do preheating, right? Preheating the substrate before you start printing. That preheating, actually, if it's done less than 200 degrees Celsius, would be quite advantageous because of the reduction of thermal gradient in the printed part. But if the I guess I'm not, I'm just talking too fast, so my throat is a little bit itchy, but nothing to worry. I just tested negative. In the old days, I would like to stay with people that are positive. I like to be with positive people, but not anymore. Now I try to stay with only negative people. Okay, anyways. So the temperature, if the preheating temperature goes above 200 degrees, we see that the flow stress actually reduces and the residual stress will increase as a result. That is a very interesting result that can be predicted. The grain size is predicted, the formation of defects. Okay, this is one biggest topic in the area of additive manufacturing. The resulting surface roughness because of the cap height, the resulting balling defects are because of insufficient energy inputs and reduced wetting ability of the material. Very undesirable. Keyhole, if the laser energy is too high or the scan speed is too low, there will be the formation of poles and bubbles inside of the part. Very undesirable. And the lack of fusion, of course, due to the incomplete overlap of heat affected zone. And this is how the surface finish is created by the cap height. And we have quite a bit of experimental data to show that it predicts quite well with our analytical prediction of surface finish under different process parameters. And this actually is our effort to show how the lack of fusion is created. Laser exposure this tracks go through the material line by line, but these scanning tracks do not overlap with one another perfectly. The yellow portion is the fuse, is the solidified portion that is very nicely consolidated, but the blue portion is not. So blue portion is not heat affected that much, and it remains as a void when the part is already scanned and built into the final product. So be able to calculate the lack of fusion. That may be a couple of second time to show our capability of predicting the lack of fusion porosity. With our model, a closed form solution nature takes less than 1 minute to complete, but with the finite element ANSYS calculation, that will take a good 5 hours of simulation. And we are also able to calculate because of the lack of fusion is a geometrical thing, so we're able to develop a threshold value above or below which the lack of fusion will not happen. And the keyhole is, like I said, is a result of high energy deposition into the material and to generate the instability of the fluid that release air bubble. And these air bubbles, unfortunately, if they do not have enough of time to escape to the free surface, they'll be caught and trapped by the moving interface between the solid and liquid, and they will become permanently embedded into the solid material and form pores. And then from the thermal history and temperature profile, we're able to calculate the characteristic velocity of those bubbles and the probability frequency of the bubbles get trapped, and calculate the two-dimensional, three-dimensional porosity as a ratio of the bubble cross-sectional area to the moving interface cross-sectional area. And that is a comparison here on the lower right of our prediction in comparison to experimental measurements. And I guess, oops. And this is the balling effect. So balling takes place when the cap height has what we call the contact angle greater than 90 degrees. So the red portion of the cap height will then fall to the sideways on the left and on the right to generate ballings. If you look at the balling to take place according to our threshold, balling will take place when the contact angle become negative or greater than 90 degrees. And then you can see balling to take place following the prediction of that threshold, and in different configuration with different materials, okay, to the left as well. So we are able, from these analysis, we're able to generate so-called the porosity map. This is an example of a combination of a process parameter, scan speed, laser power, and layer thickness. If we start from the lower right corner, there's no defect, and increase the laser power, we get into the keyhole region. And then increase the thickness, layer thickness, and increase the scan speed, we're getting a lot of lack of fusion. Or we do further higher speed scanning, we get into the defect of balling. With higher laser power, we get keyhole to show up again. So I guess, Glenn, this would be a reasonable time for me to stop. Yeah, so one last slide. So the prediction of temperature in our calculation. If you use the ANSYS finite element software, it would take about 4 to 6 hours to calculate the temperature. But in our prediction, it takes about 10-second time. Thermal stress works about pretty much the same way. So with that, let me say thank you very much for your attention. If I may entertain any questions of yours.
Yes, thanks. And yeah, we do have maybe just a couple minutes for 2 or 3 questions. So
sure.
There's one in the chat, which I will read. It says, great work. Did you use the control volume approach to generate the additive manufacturing numerical model?
Yes, that is exactly it. To control volume, the Lagrangian description of energy conservation. That's exactly what we did.
Great. Okay, and I see there's a hand raised. So if you want to unmute yourself, that'd be great.
Okay, so please. Can you hear me okay, Professor?
Very clearly, very clearly.
So, good morning, Professor. So I have several questions. So first one is, as you say, the single particle magnetic abrasive machine. This is a use magnetic file to control the magnetization particle to cut material. So my question is because this kind of technology, they will require a high accuracy magnetic file. So if the environment has other than magnetic file, like come from the laptop, come from the others, the electronic equipment, so will they impact the accuracy? So this is the first question.
Yeah. May I answer that one by one? Because at my age, I may not remember your question when you get to the third one. The accuracy is a function of the rotational speed of the particle as well as the feed rate, feed velocity of the particle. If you're willing to rotate a particle high and willing to feed the particle slow, you get much better quality, much better dimensional accuracy. So it's a variable.
Okay, so my second question is, so we know that the iron or cobalt, this kinds the metal that can be magnetization by the strong magnetic file. So when we use this kind of technology to cut this kind of metal, so how do we prevention the matrices of our magnetization? So will they for accuracy?
That would affect the accuracy as well. So the magnetization of the particle has to overcome the magnetism of the workpiece. Okay, so that can be a problem.
Okay.
Because it's not only the particle that is put in the magnetic field, the entire workpiece is also situated in the magnetic field.
Okay. Yeah. Okay. So my number 3 question is, so we know whether it's the plastic or metal, the most has a crystalline grain, this kind of structure. So the space between crystalline grain and the grain, it mostly has a lower strength. So when this magnetic particle, they are cut into the interface between grain and grain. So how do we prevent this grain, they are earlier to break off, come from the material, so make the cut face become rough?
Right. The grain boundary, we're talking about crystalline material as opposed to a single crystal material. The grain boundary does not appear to be a hindrance to cutting. It is a hindrance to dislocation motion, the way we know it, for plastic deformation. But for cutting, the grain boundary would get easily removed. So that is not much of a difficulty, the grain boundary.
Okay, so my last one question is, we know the magnetic particle, there itself also be erosion and damage when not to cut material. So my question is, when their surface become irregular, so will the accuracy or the surface quality become changed? What effect?
Yes, absolutely. The surface of the particle is meant to be irregular. If it's a perfect spherical, then there will be very little cutting effectiveness. It's meant to be irregular. And that the effective cutting radius would be the radius of the most protruding portion on the particle. So that is what we based upon, what we base our accuracy upon. This most protruding portion on the particle.
Okay, so thank you, Professor.
Thank you for your interest.
All right. Well, we are over time. So I just want to thank our speaker, Professor Liang. Thank you very much.
Thank you.
And thanks everyone for attending, and we will see you next week. Look forward to next week's talk. Thank you.
Yeah, thank you very much, Professor Liang.
Thank you all. Thank you, Wenhui. Goodbye.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.